So it's my great pleasure to introduce John Percy today. He's an extremely active retiree from two University of Toronto departments, Astronomy and Astrophysics, as well as Science Education at OISE. He was also a founding faculty member at the University of Toronto in Mississauga, where he later became vice principal. His academic work in astronomy is impressive. I count over 250 research papers and a book called Understanding Variable Stars. He's a fellow of the American Association for the Advancement of Science, of the Royal Astronomical Society of Canada, and the Royal Canadian Institute. But just as important as his work in astronomy is his work in science education, which has been recognized by his being the inaugural recipient of the U of T President's Teaching Award, being honorary president of the Science Teachers Association of Ontario, and serving as vice chair of the Board of Trustees of the Ontario Science Centre. He received the Royal Canadian Institute's Sanford Fleming Medal for contributions to the awareness and appreciation of science and technology. And to say he's an active professor emeritus is an understatement. He continues to give lectures, both academic, public, and to win awards. And I learned from his personal webpage, he's publishing 2 to 3 academic publications a year about new findings in astronomy. He's updating resources for teaching astronomy for Ontario schools. He has links to lots of public presentations up there on his website, and intriguing items like a link to a campus astronomical walking tour and a link to a site on how to teach multicultural astronomy. So I really look forward to his talk today to disabuse us of some of our misconceptions about the universe. John, over to you.
Okay, let's see if we can get the technology working here. Okay, can everyone see the screen here? Can everyone hear?
Everything's perfect.
Okay. Right, so in my public outreach, there's 2 talks that I most often give. One is called The Amazing Universe. It's a kind of frontiers of astronomy thing. But the other one is this one here about common misconceptions about the universe. And they're quite different in the sense that The Amazing Universe talks about all the frontier, exciting stuff like black holes and things like that. But this one here is much more about very basic things that you should have encountered in school or you will encounter in the mass media and things like that. And what's neat about it is that the misconceptions that I'm going to tell you about come about because of a wide variety of different reasons. And they're basically the same reasons why misunderstanding, misconception, misinformation is so prevalent in our society today. And it's something that we really need to be concerned about, is this epidemic of misinformation. So I'm kind of hoping that the presentation this afternoon gives you a little bit in terms of a vaccine against misconceptions that you may encounter, not just about astronomy, but other things. So I want to stress that by a misconception, I mean something that you know for sure, but is not correct. Because there's certainly lots of stuff that I don't know and you don't know and don't claim to know, but this is different. This is that we are quite sure that we know what the correct answer or the correct concept is or whatever. And as we go through here, you'll see that there's a wide variety of different misconceptions with different causes. And virtually everything that I talk about is something relevant to everyday life or to things that you hear about very often in the newspapers and other media and so forth. So let me start with something very basic, and these are misconceptions about astronomers. You may remember the cartoonist Unger, who did the cartoon left there. This is my rapid introduction of myself. John is an astronomer, and there's the stereotypical old man gazing up at the sky. There's another stereotypical old man on the bottom right here who's gazing up at the sky with a spyglass with a funny looking hat on their head. And I assure you that despite the fact that I'm a graying white male, it's certainly not true anymore that astronomers are graying white males. They certainly don't dress like this fellow here does, and we don't look at the sky with spyglasses. We have things that are somewhat more technically advanced than that. So I want to introduce you to some of my young colleagues at the Dunlap Institute of Astronomy, which is one part of our astronomical community at U of T here. And you will agree that we're a pretty diverse bunch, and we're always intending to become more diverse, more inclusive. This is certainly one of our great goals right now. So these are the astronomers of the present and the future. I'm not necessarily representative of all that. Okay, I want to start with the granddaddy of all, if I may use a politically incorrect term here, granddaddy. The granddaddy of astronomical misconceptions is simply, why is it warm in the summer? And you will agree that it does get warm in the summer and it gets cold in the winter, so why is that? So when I was actively doing research up at OISE, we administered little questionnaires like this to various groups, teachers, students, teacher candidates, and so on and so forth. What causes these seasonal increases in temperature in the summer? And there are 5 choices there. I won't ask you to tell me what you think the answer is, but in most general audiences, the first one is the one that's immediately jumped to. The Earth is closer to the sun, therefore it's warmer. Everybody knows that closer is warmer. Well, is that right? No, it isn't. Actually, the second one, it's because the sun is higher in the sky in the summer, though not directly overhead. And certainly, as you know, the days are much longer in the summer, typically 16 days, as opposed to something like 8 in the winter. So here's a simple diagram, which everybody should know about. This is the path of the sun in the sky during the day. And right now, this is almost the summer solstice. So the sun rising way north of east, going up very high in the southern sky, setting way to the north of west. And it would be above the horizon for about 16 hours, as opposed to in the winter when it's only about 8 hours above the horizon and never rises up much higher above the south point. So this is about as basic an astronomy as you can get. So the question is, why do people have this misconception here? And on this slide here, this is a slide from a typical school textbook. Now, this slide is actually supposed to represent the fact that the Earth's orbit around the sun is not exactly circular. We're about 1% closer to the sun and 1% further away at different times of the year. But to emphasize that, they have drawn this diagram here, which is certainly not to scale. And it certainly looks like the Earth is closer to the sun at one particular point in its orbit and much further away at another. So obviously, it must be warm when the Earth is closer to the sun and cold when it's further away. Actually, we're a little bit further away in July, which of course is when it's warm. So obviously that theory doesn't particularly happen. So the question is, why do people have this belief here? Well, a philosopher would call it Occam's razor. You always take the most obvious or the simplest answer. And certainly the simplest explanation would be that nearer is warmer, but that's not true. So never accept the simplest explanation unless you've got some evidence to pass it up. So here's another very basic concept in astronomy. Why does the moon show phases? Why does it go from new moon through first quarter, full moon, last quarter, and so forth? And here's a picture that shows those different phases here. Well, again, if you ask most general audiences, they will say, well, it's because the moon is moving into the shadow of, they know at least that the moon does not its own light, it shines by reflected light, and they assume that it's due to the Earth's shadowing. Again, that's not correct. It turns out it's just because of the orientation of the moon, the sun, and the Earth as the moon goes around the Earth. So in terms of teaching in the school, we highly recommend the sort of thing that's pictured here. That is, the kids actually go through a three-dimensional hands-on activity in which they can model the different phases of the moon. Or if you want about it, if the moon is in the opposite direction to the sun is going to be shining straight down on the near side of the moon, and you get a full moon. Whereas if the moon is between us and the sun, we're seeing the dark side of the moon. The bright side is on the other side where we can't see it. So those are the explanations for phases. Well, again, we might wonder, well, why do people have beliefs like that? And here again is a diagram from a science textbook. Now, if you look at that, your eyes will probably cross because it's actually a very bizarre diagram here. There's two sets of moons. The outside set of moons here is how the moon looks as seen from the Earth. The inner set of moons here is how the moon looks when seen from some external point of view. But the diagram isn't to scale. It's not three-dimensional. They don't tell you that we're looking at the moon's orbit at an angle, which is why it looks oval instead of looking more or less circular. Some people might think that there's actually 8 moons going around the Earth. And if you looked at the inner set of moons, you might think that the moon goes around the Earth on some kind of track like a subway track. Well, probably they wouldn't think that, but you never know. So, diagrams. Well, what does happen when the moon goes into the Earth's shadow? Well, you get something that happened a couple of weeks ago. You get a total eclipse of the moon. I don't know if any of you saw at least part of this eclipse of the moon here. It wasn't really observable in its fullest sense here in Toronto. What did happen was that the moon went from the upper right here down to the lower left over the course of a few hours, and we got this beautiful eclipse. In eclipse, the moon doesn't turn completely dark. It turns a bloody shade of red because a certain amount of light comes in bent through the Earth's atmosphere and bent into the shadow. So it was something that had profound effects in ancient times when people didn't understand what was the cause of this. So that's really what happens when the moon goes into the Earth's shadow. Well, here's another simple question here. Looks like a black and white question. What color is the moon? Is the moon white or is the moon black? I'm sure you're tempted to say that the moon is white, but in fact, you could argue that the moon is actually black. It's as black as tar in the sense that it reflects only about 5% of the light that falls on it, absorbs the other 95%, which leads to the question, why does the moon in the sky look white and why does it look so bright? Well, a simple answer would be that it's relative to the background, which is completely black, give or take light pollution, and it looks like it's white and bright to us, but it's actually. So here's another interesting question. You've all seen the full moon, you've all seen the quarter moon or the half moon. Here's another question of terminology. It's a quarter moon in the sense that the moon has gone a quarter of the way around its orbit, but if you look at it, it looks more like a half moon like this. So you might ask, well, how much brighter is the full moon than the quarter moon? The obvious answer is it's twice as bright because there's obviously twice as much area there. But in fact, it's actually 13 times brighter at full moon than it is at first quarter, last quarter moon. And there's a couple of reasons for that. One is that if you look carefully at the part of the quarter moon that's between the bright and the dark side, and that's shown on the bottom right here. You'll see that there's a huge amount of shadowing by the craters on the moon here. Whereas if you look at the full moon, which is at the top here, there's shadowing. And furthermore, the light that shines on the moon is being reflected straight backwards, which turns out to be much more efficient. But I'm sure you've all sensed that the full moon is incredibly bright. And certainly that's one of the things that you can observe even at downtown Toronto, where there's relatively few things that we can observe. Now, here's something that can spark some really interesting classroom debate, and that is whether the moon rotates or not. Because here there's a set of images of the moon at different phases here, and if you look carefully at those pictures there, you can see the famous face of the moon or the person on the moon or whatever. And you'll notice that at each phase, as the moon is going around the Earth, you see exactly the same face. So the moon is keeping the same face towards the Earth. And does that mean, therefore, that the Earth does not rotate? Well, in fact, it rotates in the same period of time that it revolves around Earth. So as it's going around the Earth, it is slowly turning so that it keeps the same face towards us. So in a sense, relative to the Earth, the moon isn't rotating, but if you observe it from the outside perspective, it certainly is rotating. And as I say, you can set this up as a classroom demonstration, or if it moves you, you can go home and actually do this demonstration for yourself. It turns out the reason the moon keeps the same face towards the Earth is because tidal forces over billions of years have caused the moon's rotation to slow down so that one face is perpetually locked towards the Earth. The moon is slowly doing the same thing towards the Earth. The Earth's rotation is gradually slowing down so that trillions of years from now, one face of the Earth will be perpetually facing the moon. And you may have noticed that every year or two, there's an extra second that's inserted into the year. And that's the reason for doing this. We also know that about 3 billion years ago, 15 hours in the day, because the Earth was rotating that much more quickly. So it's something that crops up if you're doing geology or paleontology or something like that. Now, talking about the far side of the moon, the media love to refer to the dark side of the moon as something conspiratorial. The far side of the moon, sometimes called the dark side, is simply the side that we never see. So there is something slightly mysterious about it. But remember that it isn't always the dark side of the moon. At full moon, it is. We see the illuminated side of the moon. But at new moon, we're the dark side of the moon because it's facing us, and the side facing away from us, the side facing the sun, that's the side that's away from us. So the far side of the moon is actually the bright side. But it does sound conspiratorial, and the rock group Pink Floyd did issue a very popular record called The Dark Side of the Moon many decades ago. And so it's one of these expressions that crops up in the media every now and then. Now, here's a misconception, and I love to correct this for teachers because they have the impression that astronomy is something that can only be done at night. The stars come out at night, the stars don't, so to speak. But if you go out at 4 o'clock after this talk, or at 3 or at 2:30, or whenever you get bored by this talk here, do look up at the sky on this clear day, because you just see the first quarter moon in the daytime sky in the afternoon. And the last quarter, you'll be able to see the moon at in the morning between sunrise and noon. So you should be glad to hear that the moon can be seen at those times and not just at night. Now, here's another term that comes up in the media increasingly often, because they invented this term. This is not a term that astronomers invented, and that is the supermoon. Now, the orbit of the moon around the Earth is not exactly circular. It's slightly elliptical, and so there are times in the month when the moon is about 10% closer to the Earth than average, and so it looks about 10% larger, looks about 20 brighter than average. But the fact is that you could not actually see that unless somebody told you that that was the case, or if you were able to see the supermoon and the not so supermoon at exactly the same time, side by side in the sky. So it's no big deal. So if you read in the media that it's going to be the supermoon in 1 week, don't expect something really significant or spectacular. On the other hand, a few years ago, we arranged an event on campus, and here's our dearly beloved main campus here. There was going to be an eclipse of the supermoon. So we had an event which attracted almost 10,000 people, even though it was mostly cloudy, as you can see in the sky. But there were dozens of astronomers there for people to talk with, and we had lots of other interesting things for them to do. But it does show that the term supermoon will bring out a crowd. Now, here's something that I'm sure you've all seen, and that is that if you see the moon close to the horizon, it really looks as if it's humongous. It really looks as if it's bigger than it normally would be. Well, you can test this quite simply by going out with an aspirin in your hand and holding it between your fingers at arm's length, and you'll notice that the aspirin exactly covers the disk of the moon. And if you wait 6 hours until the moon has risen and is high in the sky, you can do that experiment. You'll find that the moon is exactly the same size when it's high in the sky as when it's near the horizon. But it's a very famous optical illusion. It's one of the most famous optical illusions as far as psychologists are concerned. It has something to do with the fact that when we see the moon near the horizon, we're seeing it against nearby reference things, buildings and skylines and trees and so forth, as opposed to by itself in the sky. And by the way, if you don't believe in optical illusions, just look at this and tell me which of those two blue circles is the largest one. And of course, yes, they're equal in size, even though the right-hand one looks bigger than the left-hand one. Okay, now getting into somewhat more serious things here. You've probably heard that there is more crime and madness at full moon than there is at other times. And that, of course, has created various myths over the ages. It's a quite widely held misconception. And the cause of that seems to be, because there's no evidence that it's actually true, is something called positivity bias. And that is that if you see a crime or madness occurring at full moon, when you can see the full moon, you record that fact and you notice it. Whereas if you see the same thing happening when the moon is not visible, you don't record that the moon was, you don't ascribe the madness of the crime to the moon. And it's one of these things that does apply to other fields as well. We certainly hear when some drug or some vitamin has a positive effect on some disease or on our health in general, but many things have been tested and found to have no effect on a disease or on our health or whatever. And unfortunately, we rarely hear about that, even though it's actually important information to have. Here's another of the very, very popular misconceptions here. You've all heard the term weightless, and the fact that astronauts in the space station feel weightless. They can float around, like this picture of Chris Hadfield here, who's juggling balls or tomatoes or something like that. And the misconception is that this occurs simply because there's no gravity in space. I remember going to a UN conference at Vienna on space activities, and there was an exhibit by the Canadian Space Agency. And without announcing myself, I sort of asked the people that were manning this particular exhibit here, is it true that there's no gravity in space? And 2 out of 3 said, yes, it's true. There's no gravity in space. But actually what's happening in the space station here is that the space station and the astronauts are falling towards the Earth because of the Earth's gravity. And luckily, they're going sideways at about 10 kilometers a second, which carries them in an orbital path so that they don't actually fall to the Earth. You can be weightless for at least for about half a minute. If you go up to the top of the CN tower with a phone booth, stand in the phone booth asking your best friend to push you off the side of the CN tower, and for about half a minute you will be weightless. There'll be no pushing up of the floor of the phone booth of your feet, but please don't do that. Definitely not to be recommended. But there is gravity in space. That's what causes the space station to orbit around the Earth. That's what causes the moon to orbit around the Earth, et cetera, et cetera. Now, here's the granddaddy of all conspiracy theories here, and that is that about 1/6 of Americans believe that the Apollo moon landings never happened. They were all staged in a movie lot in Arizona or somewhere like that. And that's rather unfortunate. But you have to ask, well, do they have any evidence for this? And if you look at this picture here, and you've probably all seen this picture, you'll notice that the American flag is flying, even though there's no air on the moon. Therefore, there can be no wind, and there can be no way that the wind is causing the flag to fly. So why then is the flag flying? Well, the answer is fairly simple, because if you look at the, if you look at the top of the flag, you'll notice that there's a piece of rod there, just like a curtain rod, that's making sure that the flag is clearly visible to the billions of people around the Earth, and that everybody knows who it was that spent $80 billion to put astronauts on the surface. So the Apollo mission did take place. You may not know that all the studies of the Apollo moon rocks were, for magnetic purposes, were done at University of Toronto, Mississauga, because we had a nice rock magnetism laboratory, and no streetcars or subways going by every 2 minutes to disturb the studies there. So that was one of U of T's important contributions to the Apollo moon missions. Here's another misconception here, and that is that the planets in the solar system are all lined up like this in a straight line and very close together. It's certainly a very convenient diagram here, because you can show all of the planets there. They're actually more or less to scale, but the fact is that the solar system is much more spread out than that. If you made a model of the solar system where the sun was a beach ball, then the planets would be scattered out by about 2 kilometers direction. And by the way, there's at least one scale model of the solar system in downtown Toronto. I've never actually walked the whole thing there, but one community has decided to make a neat scale model in their neighborhood, depicting the actual distances of the planets from each other and their relative sizes. Here's another picture from a textbook here, and this has to do with the asteroids, these small minor planets that orbit the sun between the orbits of Mars and Jupiter. Now, if you look at this diagram here, you might think that it's going to be a heck of an undertaking to try and get a spacecraft going from Mars to Jupiter without running into all of these asteroids here. Well, the thing is that the asteroids are not nearly as densely packed as they seem on this picture here. I'm rather fortunate that an asteroid is being named after me, and if I was standing on my asteroid, I could look out in all directions and I would not see any other asteroids in anywhere nearby. But if you've ever seen those Saturday morning cartoons that the kids watch, then there's always some intrepid hero who's piloting their spacecraft, dodging asteroids back and forth as they try and chase whatever villains they're chasing. In fact, here's a diagram here that's taken, as I remember, National Geographic magazine of all things. And it reinforces virtually every misconception about the universe that I can immediately think of. You'll notice the planets are all packed closely together, going around the sun on their railway tracks here. The asteroids are thick and fast here between Mars and Jupiter. Just outside the orbit of Neptune, you can see the stars just outside the solar system. And not very far away in the upper left-hand corner is a nearby galaxy of stars. So you can't help wondering why people have misconceptions about how the universe is spaced out. Well, you remember that when you were all younger and I was younger, there were 9 planets in our solar system, and the 9th planet was Pluto. And I was there about 20 years ago in Prague when the International Astronomical Union demoted Pluto for being too small. And it was decided that Pluto was too small to be a planet, especially as other Pluto-like objects were discovered in the outer solar system. And on this diagram here, the 2 leftmost objects there, Sedna and Quaoar, are almost as big as Pluto. They're what we call Kuiper belt objects. They are made mostly of ice, and there are many of them. And the problem was that if you call Pluto a planet, you call Sedna. Sedna is the 10th planet or whatever it is. And so it was decided to draw the line below below Mercury. Anything bigger than Mercury was a planet. Anything smaller than Mercury, including Pluto, was not a planet. They became called dwarf planets, and that's what we call them. But when Pluto was a planet, then any suggestion that there was a 10th planet became planet X, X being 10, of course. And X is a very conspiratorial thing. Think of the X-Files and so on and so forth. So there were all sorts of conspiracies about NASA hiding another planet behind the sun, or some other place where nobody had seen it and they knew about it, nobody else did. So another example of a conspiracy. Okay, changing topics a little bit here. Here's a beautiful picture, and the question is, what is this and what is it doing? Well, many of you may recognize this as a comet, and I'm sure you're tempted to think that this comet is streaking through the sky from the upper left to the lower right, its tail behind it. But first of all, it's not streaking. Secondly, its tail is not trailing behind it like a cat's necessarily. Because here's a chart about a comet a couple of summers ago called Neowise. And this is the chart of its path across the northern sky from July 15th to July 31st. And you'll notice that in 2 weeks, it goes more or less twice the size of the Big Dipper. It takes about 1 week to go a distance equivalent to the size of the Big Dipper in the sky. So that's not exactly streaking. And furthermore, you'll notice that the tail of the comet is actually pointing ahead of the comet like a searchlight. And that's because the tail of a comet actually gases that are pushed away from the comet by the radiation of the sun. So the tail always points in a direction opposite to the sun, even if the comet is going away from this comet was here, and the tail is actually pointing away. So the question, of course, is why do we call it a tail if it's on the front of the comet as often as it's on the back? Certainly my cat's tail is on the back, and it would be very strange if its tail suddenly appeared on the front. Well, a lot of people confuse comets with something else called meteors. Meteors are familiarly called shooting stars or falling stars, and some people do actually think they have something to do with stars, which they don't. A meteor is a small chunk of space rock, sometimes only the size of a sand grain, passing through the atmosphere at 30 kilometers a second, burning up, burning its energy into the light that we see. And it certainly does streak. It takes about 1 second for a meteor to streak across the sky before it burns up. But it has nothing to do with stars. Well, speaking of stars, you remember that National Geographic picture that I showed you that implied that the stars were just outside the solar system. And this is certainly not true. The nearest star to the sun, Proxima Centauri, shown on the left in an artist's conception here, that's about 10,000 times further away than Neptune, which is the most distant planet. On that scale model that I suggested, where the sun was a beach ball and the solar system planets would extend about 2 kilometers in each direction, the next nearest star on that model would be in New Zealand. So there's a great distance from the outer solar system to the nearest star. Incidentally, the nearest star, which is to the left on this artist's conception here, not only has a planet, but it has an Earth-like planet. So the fact that the nearest other star to the sun has an Earth-like planet suggests strongly that Earth-like planets are very numerous in the universe. And this is one of the most exciting developments in astronomy in the last 20 or 30 years. So we have to use telescopes to study the stars. We can't easily send a spacecraft to the stars. And this is the telescope, the Dunlap Observatory, which was part of the University of Toronto. It's now owned by the city of Richmond Hill. And if you look at advertisements in the paper, you'll notice that telescopes are traditionally advertised as by their magnifying power, 99 power, 999 power, or whatever, and for only $99.99. Well, the fact is that the magnifying power of the telescope is not of any interest to astronomers. We use a telescope to gather light and to bring its sharp focus so that we can see detail. You can achieve a high magnifying power simply by putting a very strong eyepiece on your telescope. So if you want to buy a cheap telescope from a department store, you may get high magnification by magnifying an absolutely cruddy image there. We call these trash telescopes, by the way. Please don't get a telescope for young people that you know at Christmas time unless you check very carefully with a knowledgeable source. Okay, so on to the stars here. You may have thought that the stars are all white, that they all have the same color there. And they certainly tend to look that way, and that's partly because the eye has very little color sensitivity at low light levels. But you'll look at this picture here. This is the famous constellation Orion. You'll all agree that the upper left star is reddish and the lower right star is bluish. Those are Betelgeuse and Rigel. And a star is reddish because it's cool, and it's bluish because it's hot. So it's exactly the opposite to the taps in your bathroom. You can bring out the colors of the stars by using your binoculars because you get a higher light level there. It's one of the good useful purposes for binoculars if you happen to be a nature lover there. But unfortunately, Orion has just left us for this season, and it will be back in the fall. Another little observation you can try is look at the Big Dipper, and there's one star in the Big Dipper that has a slightly different color than the rest. See if you can identify it. There's one star in the Big Dipper that has a slightly different brightness from the other 6. See if you can identify that. So lots of things that you can do even under city lights. Okay, here's a fairly simple question here. If I ask a general audience, do they know what the brightest star in the night sky is? They will invariably say Polaris, mainly because that's about the only star that they know of in the night sky. They know it's very useful. It's almost directly north, as every Girl Guide or Boy Scout should know. The angle of Polaris above the north point is very nearly equal to your latitude, so very useful for navigation as well. But brightness-wise, it's number 47. Number 47. Brightest star in the night sky is Sirius. Seriously, that's true, but not Polaris, unfortunately. I could go on for an hour about Polaris. It's one of the most interesting stars in the sky as far as astronomers are concerned. Of course, in the daytime sky, the sun is the most interesting star. It's the only star that we see in the daytime sky under normal circumstances. You may have heard that it's an average star, and the fact is it's not. Our sun is bigger and brighter than over 90% of all stars in our galaxy. Most of them are what we call red dwarf. So we are well above average, but we are a normal star. Our star is normal in the sense that, like all the other stars, it derives its energy from converting hydrogen into helium by a process which astronomers unfortunately refer to as hydrogen burning. And so people might think that the sun was on fire, but it's not burning in a chemical sense. The sun is actually too hot for chemical burning. All of the molecules would be broken apart into their constituent ions and electrons. So remarkably, the sun shines by nuclear fusion. It produces 400 million watts and has been doing so for 4.5 years. Obviously a quite remarkable star. Well, you may also know that a few days ago there was an eclipse of the sun. Not a total eclipse, but what we call an annular eclipse. It was visible from northern Canada, but it was only visible as a partial eclipse down latitudes. I hope maybe 1 or 2 or 10 or 20 of you got up early in the morning on Thursday to observe the partial phases of the eclipse here. But one thing that you've probably heard, and in fact, I hope you have heard, is that you should never look directly at the sun with your unaided eye, and certainly not with binoculars or a telescope. But when people are tempted to look at the sun, when a total eclipse occurs, then they do have some reason to do it, which they don't normally. And so we get notices from school principals saying, make sure the kids hide under their desk for the entirety of this eclipse here, because there are deadly radiation emitted by the sun during this eclipse. Nothing special emitted by the sun during an eclipse, other than it happens to be a rare and very beautiful phenomenon. For those of you who are going to be around for a few years, there is going to be a total eclipse of the sun in 2024, not visible in Toronto, but a few, maybe 100 kilometers away in Niagara Falls or Buffalo. You will be able to observe this as a total eclipse. And I can guarantee you that thousands of people are going to be going there and making hotel reservations, pandemic permitting, of course, for that eclipse in 3 years from now. Okay, moving towards the end here to more modern ideas. You've all heard, I think, of black holes, one of the interesting astronomical phenomena that's made it into popular culture. You may know that a black hole is something whose energy is so strong that nothing can escape, not even light. You may not know that the first black hole in space was discovered at the Dunlap Observatory of the University of Toronto in 1971 by my colleague Tom Bolton, who sadly passed away a few months ago. And so this is an artist's conception of what that black hole looks like. It's actually part of a binary star system. The black hole on this artist's conception is on the lower right, surrounded by a disk of gas streaming into it from the normal star, which is the one on the left here. So a very, very small amount of gas is streaming into the black hole there, becoming very hot, producing X-rays, and eventually disappearing into the black hole. But the amount of material that does this is actually minimal. It's about 1/1000th of the mass of the visible star. But it does raise the misconception that somehow black holes are cosmic vacuum cleaners that go around eating up everything in our galaxy, including potential sun and solar system. But the fact is that the black hole only affects things that are very close to it. And as you remember from that model that I told you about of a model of the solar system and the nearest star, the stars are very, very, very far away from our solar system, and black holes are not going to come around and eat our solar system. Speaking of such things, if you still have your original version of Trivial Pursuit, it says that the end product of the sun's evolution will be a black hole. The sun will turn into a black hole at the end of its life. This isn't true. The only stars that become black holes are very, very rare massive stars, maybe one star in a billion in our galaxy. Our sun will end up, as shown on this slide here, on the left here. The outer layers of the sun will slowly drift off into space, leaving behind something called a white dwarf. You may see that white dwarf right at the very center of this nebula here. This is called a planetary nebula. It's a star at the very end of its life, a star like the sun. So this is very much like the sun will appear 4.5 billion years from now, when it finally runs out of energy. Its core slowly shrinks to become a white dwarf. The outer layers drift off into space, become part of the material that will form the next generation of stars. Here's another term that confuses people a great deal, and that's the light year. I mean, we say that the University of Toronto is light years ahead of any other university in Canada. Well, not quite, but a light year is actually, despite the term, a unit of distance. A light year is the distance that light travels in a year, traveling at 300,000 kilometers a second. So it's about 10 million kilometers, and turns out to be a very useful unit of distance for astronomers, because on this picture here, showing a typical galaxy like our own, it's about 100,000 light years across. By the way, that it takes light 100,000 years to go from one side of our galaxy to the other. Therefore, if you live on one side of our galaxy, you see the other side as it was 100,000 years ago. You literally are looking back into the past. But again, a misconception that comes from the terminology that we use. In fact, it turns out that you have to be careful to explain to people what the difference between a solar system, a galaxy, and a universe is. This is a picture of a galaxy, but many people might think it's a solar system in formation, or many people might think this is what the universe looks like. In fact, the universe has tens of billions of galaxies like this in it. Which brings us to the Big Bang. This is the slightly derogatory name for our present, for the birth of the universe 13.7 billion years ago. And so many people would envision this as that the universe suddenly exploded into pre-existing empty space, sort of like a firecracker going off in an empty room or something like that. And this artist's conception here on the left is that picture very well. But according to Einstein's general theory of relativity, that's just not the way that things are, in the sense that matter is part of space. Space and matter are closely connected together, as is time. And so the Big Bang was really the beginning of the universe, of space and of time. And space is expanding, carrying everything with it. So a good analogy is this balloon here. This is a kind of two-dimensional analogy to our three-dimensional universe. But if you imagine the young universe on the left here with the galaxies on the space of the balloon, and as the balloon representing space expands, then the galaxies stay in the same place relative to space, but they do move apart, as we observe the galaxies doing, because of the expansion of space along with the matter in it. Okay, this brings us to the last three subtle misconceptions, and these are things that you're very, very familiar with. And first, of course, is astrology, the idea that somehow the positions of the sun, moon, and planets have some influence on human events and behavior, and can perhaps even predict the events and behavior in the future. Well, we always need to be evidence-based here, and numerous studies, including ones that astrologers have helped to design, show that astrology has no astronomical basis. That is, it isn't in the stars. Astrology has nothing to do with it. On the other hand, we do know that people subscribe very strongly to astrology. We know that both of the Toronto Star and the Globe and Mail have horoscope columns for entertainment only, they assure me. You may know that there was a scandal in the a few months ago because it turned out the astrologer was recycling their horoscopes from one month to the next, and they got turfed and replaced by yet somebody else. And in fact, yet somebody else is taking over that particular column. But the interesting question is, why do people subscribe so strongly to astrology? And the answer may be that it simply gives them good advice. So whether it has anything to do with astronomy or not, that doesn't matter. There's something very strong called the placebo effect, very well known in medical science. And that is the idea that if people think that they are receiving some therapy or treatment for their ailment, they may well feel better. So this is a quite real thing. It's like an optical illusion. It's something that's very real to our own minds. And people do like a sense of identity, that they're a Leo or they're a Cancer or whatever, and the sense of belonging. There's a sort of tribal nature to all of this. But the point is, it has nothing to do with astronomy or the stars. Another widely held belief, as you know, is that space aliens have visited the Earth and may be doing so now. I mean, try and estimate the trillions of dollars of media the expenditures that have been made on the sort of movies, television shows, science fiction books, and so forth, all having to do with this widely held belief that space aliens have actually landed. I'll tell you right off the bat that there's nothing I would like more than to know that there was life elsewhere in the universe. And it would be extremely exciting. In fact, it would be world-shaking if a sample of extraterrestrial life actually did land somewhere on the Earth, like on the front campus of the University of Toronto. So it's something that's so ingrained in popular culture that you can't help half the people in North America for believing that somehow the flying saucers have actually landed. And in fact, it's something that has resurfaced in the last few months. There was a quite good article in the New York Times a couple of weeks ago about this. And so it's something that's, in fact, there was a report presented to the US government just a week or two ago saying they'd done yet another study to see whether there was any firm evidence that aerial phenomena were of some potential danger to us, and they couldn't find any such evidence. Going along with that are the books of people like Erich von Däniken, who's made literally millions of dollars from the claim that things like the pyramids and the statues of Easter Island and so forth were actually built by astronauts thousands of years ago. And sadly, the documentaries that were based on books still appear quite regularly on channels with names such as the Learning Channel or the Discovery Channel or whatever. Very unfortunate. A more complicated question is this one. The belief that the universe, life on the Earth and life on it were created in their present form 1,000 years ago. Well, this, of course, is based on one particular interpretation of one particular scripture of one particular religion. But it happens to be a religion that has a fair amount of power, particularly in the United States. That is fundamentalist Christianity. And it's based on a reading of the of Genesis, basically counting up the begets in the history of life on Earth. Now, the evidence for an ancient evolving universe is so overwhelming that it would take days and days and days to present a complete account of all the different reasons why all of the different branches of science are consistent with the idea that the universe is 13.7 billion years old and that it and life on Earth are constantly evolving. The point, though, is that science and religion need not conflict. I look around my own department. Colleagues is a Jesuit, another is an evangelical Christian. My office mate is a practicing Muslim, etc., etc. And there's absolutely no problem in their cases of combining science and religion. They have different places within our culture here on Earth. So that brings us, and if you reflect on this, you will realize what all of the implications of this are for us to think about. Who are the people in society that one respects, that one gets information from? How do we view the media as reputable or otherwise? And there's nothing quite like finding out the truth for yourself by either investigation, if it's a classroom situation, or simply using the evidence and critical thinking. Which of them are reliable? But this is more important than ever before. As I said at the very beginning, there's misinformation in life, too much suspicion of government and of science, and we have a certain we have a certain part in being responsible for that. But evidence-based science and critical thinking is absolutely important to our health, environment, our planet, and society. We're very fortunate in Canada. We hear of journalists who are absolutely first-rate at dealing with these topics. Certainly Tim Caulfield from the University of Alberta, Ivan Semenuk, the science reporter for the Globe and Mail, who's a graduate of our astronomy department, Andre Picard, one of the best health journalists in the world. And these are people that we should pay attention to. So I always end with this slide here. Mr. Osborne, may I be excused? My brain is full. This is time for your much needed break here. And here's a few resources that you might make use of here. john.percy@utoronto.ca. I have a webpage that the introducer referred to here. One version of this particular talk is there with this URL here. And I have a colleague, Neil, who's written a sort of definitive book about astronomical misconceptions called Heavenly Errors. I think on his website he has 1,500 astronomical misconceptions, which you may or may not be interested in. Okay, so I've used up my hour here. I understand that now you get a rest, and I will be here for discussion questions about anything to do with what I've talked about or not talked about in this particular presentation here. So thank you very, very much for your attention, or not.
Thank you, John. Thank you, John. And I forgot to mention in the introduction, we really want to thank you for stepping in at the last minute when the original speaker scheduled for today canceled because of the CAUT Center. So thank you so much for the talk and for doing it on short.